All right, I hope you got your party pants on because this is the last problem in Chapter 15. And it's a good one, too. So there is one more after this, but they're really the same kind of problem, and I like this one better. So we're going to do this one, and that's it. The end is in sight. This is similar to a homework problem. It's like, I think maybe even the last homework problem that's going to ask you for concentration of all ions in solution after this reaction has reached equilibrium. So whenever you hit that one in the homework, it's, I think, the last one. Look back at this guy. You're going to do kind of the same thing. Here's kind of what we're doing. And you probably have done this reaction before, which is why I wanted to do this problem versus the last one. Do you remember taking lead nitrate, mixing it with some sodium iodide? These were solutions. They were aqueous solutions. You probably did this maybe in first year. It was a double replacement. You formed some sodium nitrate and some lead iodide. I2. Of these products, everything with sodium, everything with nitrate is aqueous. And so again, that's all you need to kind of know. Like for solubility rules, if I did this double replacement and they asked me, what is the identity of the precipitate? I know that everything with sodium and nitrate is aqueous. So kind of by process of elimination, this lead iodide must be my precipitate. Last year, they had to memorize like all the solubility rules, so they had to know that lead iodide was a precipitate. They're not going to give you anything crazy now that the other compound will obviously be soluble. Something kind of like this. We would balance it. It balances pretty slick. There we go. Done. This is that one that makes a big bird yellow precipitate. It's like super bright yellow. It's crazy. You got the lead nitrate, sodium iodide. They're clear, colorless solutions. You mix them together, and it gives you this crazy bright yellow precipitate. Everybody wants to touch it. That's bad because then you got lead on your fingers, and then you probably go to lunch and lick your fingers. Anyways, here's the formula equation. Maybe it would be fun to bring this down to net ionic. Net ionic cancels out any spectator ions. So any ions that are aqueous on both sides, that will be the sodium, you are a spectator, and the nitrate, you are a spectator. There'll be ions in solution, both reactant and product side. So the net ionic equation would really just be the lead plus 2 ion, that's in solution, reacting with the 2 iodine ions, forming that lead iodide precipitate. I2 solid. There's the net ionic. Well, that was fun. Blast from the past. Ooh, that was chapter 4, too. That was fun. Wow, this was a combination of chapters 4 and 15, the two beasts of the year. All right, let's answer some of this. We want to know the equilibrium concentrations of all ions in a solution formed by mixing the lead nitrate and the sodium iodide. They do give me a KSP for the solid lead iodide. Now, it's not going to ask you this, and you probably kind of know the answer. But, like, what if the question kind of said, will a precipitate form? Will that lead iodide really form a precipitate? What if you're like, I don't remember that big bird yellow precipitate? Here's what we would do. We probably want to recalculate the molarities right away so we don't forget to do it later because we are joining volumes. So let's do the lead nitrate. Lead nitrate. The original molarity is 0.0500. The original volume is 100 milliliters. I want to know the new molarity when I join volumes. So what do I got? 200 milliliters of the other solution for a total of 300. Let's recalculate that M2. M2, 0.0167. 67. And now, again, like, this is the lead nitrate solution. The only ion that I'm really going to care about is the lead. So that would be the molarity of the lead. The lead ion would be 0.0167 because there's one lead per particle. Now we got to do the same thing with the sodium iodide. NaI. The sodium iodide is originally 0.1 molar. It was originally 200 milliliters. I want to know M2, the new molarity at 300 milliliters. M2. Plug that in. 0.0667. 667. And so again, technically that's the sodium iodide molarity. But of the two ions, the only one I really care about is the iodine. Okay, so we're gonna kind of do this like we did in the last problem. Will it precipitate form? Let's calculate Q. Q, or kind of like the ion product. Let's see here. If I look back at my net ionic, there, I'll keep that up there. Cute. I take my initial molarities. Let's use the lead. 0.0167 molar lead. In the equation, we're just going to raise that to the first. And then I take my iodine. Here's what I have. 667. Molarity of the iodine ion. And in the balanced equation, I need to raise this to the second power. Now again, we're not going to double it yet. Because this is Q, like we're just using our initial conditions. This is what I have. I don't know that this is equilibrium. I'm going to guess that it's probably not. And we can kind of predict which way this will shift if we're not at equilibrium. Q is 7.43 times 10 to the negative fifth. They give me the K value. Where are you? Whoa! K is tiny. Q is too big. Q is bigger than K. The ion product is too large. So how do I reduce the ion product? By forming a precipitate. So if they ask me, I would say yes. A precipitate forms. Whoa! Which is kind of what we expected. If you've ever run this reaction, a precipitate really does form. All right, so now let's look at what they actually ask for in solving this question. I'm going to stop this video and start another one so that it'll load a little quicker for you. I don't want this one to get too long. So I will be back in like 2 seconds.